Okay guys, let's take a look at our lesson for today. We're going to look at the second derivative test. We went over the first derivative test, yesterday or the day before, I can't remember, and I love the first derivative test. That's the first test that I would use. The second derivative test, though, is our backup test. If there is a reason why we can't use the first derivative test, which actually I'm going to show you, there will be instances where you can't, we would fall back on this one. So let's talk about it, see how it works. We have, first of all, we are told that the second derivative has to be continuous on the open interval that contains wherever we are looking for. It has to be open. So second derivative is continuous on the open interval that contains whatever x value we're looking for. Our first criteria is that the first derivative is 0. Okay. Now, I had questions earlier today about critical numbers. This doesn't mean all the critical numbers, right? This does not include where the first derivative is undefined. It only includes where the first derivative is 0. So these are what kind of points? Stationary points. It only includes stationary points. It does not include singular points. So please keep that in mind when you're working with this test. It's just when the first derivative is 0. So that's our opening criteria, which since we need to know if the first derivative is 0, it's just so natural to just do the first derivative test, right? You've already got the zeros, so you're like, why would I do the second derivative test? And there are reasons, so we'll look at that in a minute. So what the test tells us is if the first derivative is 0 at this particular value, whatever that x value is, and the second derivative is negative. Now let's think about that for a minute. What does it mean for the second derivative to be negative? As concave down, right? So let's draw, so this means concave down. So if I have the first derivative being 0, which we know that is where it's possible to have maxes and mins, if the first derivative is 0 and the second derivative is negative, in other words it's concave down, what kind of extrema do you think I'm going to have? A maximum, right? That's what I'm going to have. I'm going to have a local maximum there. Okay, our second part is if the first derivative is 0 and the second derivative is positive. Again, let's think about what that means. Second derivative being positive means we are concave up, and so it would look like that. If we're concave up, then what type of extrema do you think we would have there? A minimum, and that's what we do. So that hopefully will help you memorize how to figure that out. If our first derivative is 0, second derivative is negative, we have a max. First derivative is 0, second derivative positive, we have a min. There is a third option when we work this test. There is something else that can happen. If the first derivative is 0 and the second derivative is 0, the test fails. It doesn't tell us anything. It doesn't tell us anything. So it's basically, if that happens, we would have to resort to some other means to figure that out. We wouldn't be able to use the second derivative test, which is another reason why it's not my first test that I would go to, is because it's possible for it to fail. It doesn't mean that there's not a max or min there. It just means that we can't determine. We don't know. We'd have to figure it out a different way. All right, questions on that test? All right, let's practice it. We're going to use the second derivative test to find where the relative extrema occur for this particular function. All right, so in order to do that, we need the first derivative. We need to find the first derivative and set it equal to 0. So our first derivative would be 15x to the fourth minus 15x squared. We would set it equal to 0 and factor. Okay, so x is 0 and x is plus or minus 1. That's where the first derivative is 0. If you want to do a sign chart here, you could, but is that necessary for the second derivative test? No, it's just necessary that we know what where the locations of the zeros of the first derivative are, not the signs. We don't have to do a sign chart here. It would be kind of fun, but we're not going to do that. All right, so that is the first part. Second part is finding the second derivative. So let's do that. So that would be 60x cubed minus 30x. All right, and we also, there are two ways. I'm going to go ahead and do a sign chart on this one. There are really two ways to determine this. Let me explain that in just a minute. Let's do a sign chart. Let's go ahead and factor out the 30x. And our locations of zeros for the second derivative are 0 and plus or minus 1 over root 2. Now, I prefer doing a sign chart here. I had a question earlier today. Can we simply substitute these values into the second derivative? And the answer to that is yes. Sure, you don't have to do a sign chart. You can just take these values and substitute them into the second derivative and determine what signs they have. That's fine. I'm going to go ahead and do a sign chart just because I like to avoid lots of arithmetic. But maybe it's easier just to sub in. It's your choice. It doesn't matter to me. So let's deal with x equals 0 first. We know that x equals 0 is one location where the first derivative is 0. And in the second derivative, what is it? It's also 0. What does the test tell us about that? Nothing, right? The test fails. So we would just say test fails. We were required to do the second derivative test, and that's what we're doing. We're just doing the second derivative test. Okay? It fails. We're done with that one. All right, let's look at when x is 1. So we know x is 1 basically here. That's where we got that number from. Over here, 1 would be in this area, right? So the second derivative is positive. So if the second derivative is positive and the first derivative is 0, what do we have? Yep, the second derivative is positive. That means we are concave up, right? Concave up gives us a minimum. So we would say, are they using, yeah, we want to use the same words they do. So relative minimum, because, of course, we're going to have to justify, because f prime of 1 equals 0 and f double prime of 1. So we have another piece to this. And unlike the first derivative test, we have another piece. What is the second derivative, the value of the second derivative? It's greater than 0. So that's why we have a minimum, because it's concave up, and like we were talking about over here. Concave up, it's a minimum. All right, our last one, -1. Let's see. All right, where -1 would be over here, right? Be over here, and so our second derivative is negative. Our first derivative is 0, our second derivative is negative. What does that mean for us? It's a maximum, right? Because the second derivative is negative, it's concave down, and so it's a relative max. Because f prime of -1 is 0, and f double prime of -1 is less than 0, right? It's less than 0. So this is our first try, or our first problem where we have to use the second derivative test. Are we okay with that? Okay. All right. Now, the second problem that we're going to be working is one, see, the AP guys love the second derivative test. They love it. They like to come up with ways where we can't use the first derivative test and we have to use a second derivative test. The second problem we're going to look at is styled off of an AP problem where they've done that. And so let's look at when we couldn't use the first derivative test. Because to me, the first derivative test is much easier. All right. This would be an example of when we can't use the first derivative test when we don't have an equation. We don't have an equation to be able to use, that first derivative test. All right, so let's see what this is wanting us to do. Suppose that the function f has a continuous second derivative for all x. What do you think it is they're doing right here for us? They're setting up our criteria for being able to use the second derivative test. If you remember from that test, it said in order to use this, the second derivative has to be continuous. They're telling us right there it's continuous. So they're giving us the go-ahead. Use the second derivative test. Then they give us some random, at this point, we think these are random numbers. We have no idea what to use them for, so let's just kind of keep them on the side. Let g be a function whose derivative is given by, we have this. Does g have a local maximum or a local minimum at 3 justify? All right, so what would we need to do? We would need to determine the zeros of the first derivative, right? We need to determine that. They're telling us that to figure it out at x equals 3, but they're not telling us that that means that there's a 0 there, that the first derivative is 0 at 3. We have to prove that. All right, so I'm going to have to take the first derivative and set it equal to 0. The second thing that I need to do is find the signs of the second derivative. So I'm going to have to take the second derivative and work with it. Doesn't really matter which one you do first. For whatever reason, I set it equal to 0 first. So let's set the first derivative equal to 0, and let's solve. All right, so 0 equals x squared minus 9, 2f of x plus 5f prime of x. So as we're accustomed, when we have a product and we're solving, we set each piece equal to 0. So x squared minus 9 equals 0, and 2f of x plus 5f prime of x equals 0. Here we have plus or minus 3. This is unknown. We really don't know anything about that. Maybe we'll be able to figure out something, but it actually doesn't matter because we have now established that where they were wanting us to look, which is at 3, the first derivative is 0 at 3. So we've got the first piece done. Now we move to the second criteria, and that is I've got to figure out what the sign of the second derivative is at 3. So I need to find the second derivative. This is a product, so I'm going to have to use the product rule. So fg plus fg, first things first, second things second. Okay, so let's use the product rule. So we take the derivative of the first piece, which is 2x, copy paste the second piece, plus copy paste the first piece, take the derivative of the second piece. Now I still have some students that are quite disturbed by taking the derivative of 2f of x. I hope we are kind of getting past that. Remember, 2 is just a constant. It's okay. You don't have to use the product rule on that. So the derivative of 2f of x would be 2f prime of x. That's it. 2f prime of x. So 2f prime of x plus, and then if it's 5f prime of x, what do you think the derivative of 5f prime of x would be? Yes, 5f double prime of x. So it's really not that tasking. We just need to be sure we understand how to deal with the constants. All right, so we have the second derivative. Now we are ready to interpret. We're really worried about this. That's it. X equals 3. So we're going to go through, and I'm going to put in, evaluate it for 3. So g double prime of 3. So the first one is 2 times 3. We'll do that in a moment. Then I have 2 times, let's see, what would f of 3 be? F of 3 is right here, and it's negative 4. Plus 5 times, let's see, f prime of 3 would be 1. Plus 3 squared minus 9. Now what does this do? What does it do to this whole thing right here? It just wipes it out, right? Because that's 0. So if that's going to wipe this out, I'm okay if you don't fill those numbers in. It's 0. 0 times anything is 0. So we don't need to, luckily, that's very nice of them to make that 0, so that wipes that whole piece out. All right, so we have 6 times negative 8 plus 5. And let's see, what is that? Negative 3, so negative 18. So our second derivative at 3 is negative 18. All right, so let's think about this. Using the second derivative test, at 3 the first derivative is 0, and at 3 the second derivative is negative. What does that mean to us? It means it's concave down, right? Negative's concave down, so it's a local maximum. And what they're using local. So we would say, so there's a local max at x equals 3. because our justification, because g prime of 3 is 0 and g double prime of 3 is less than 0. Or you could even say negative 18 if you want to, but this would be our answer. Now right here I want to give us a caution. On the AP test, they are very, very picky about naming. If we had written over here because f prime of 3 or used f, we wouldn't have gotten credit for our justification because it's asking about g. So we really need to be cautious about that and don't just automatically write f of everything. We've got to be sure we are naming the function that they are. They love to write like h of x and all kinds of different letters to make sure that we know what we're talking about. So please be sure when you're doing your justification that you use the proper naming, the proper function. Okay, does that make sense? All right. Any questions? We okay?